motion in one dimension. So what does that mean? That means an object is moving along a straight line. That's one dimension. And you can imagine it to be a number line or the x-axis, maybe referred to. It could be going in any direction, but when you're saying one dimension, you're just worried about one line. And we study it by drawing it as a horizontal line because we're not worried about other dimensions. The particle will stay on it. Okay, you could draw it vertically also if something is falling, right? If you have a free fall, you can draw it that way as well, and that is okay. So where is the particle on this line? That is its position. Okay, and whenever we measure something, you always need a reference. There is no meaning to anything, any quantity, if you don't have a reference. What's the meaning of 1 meter? Earlier, there was a piece of metal at a certain temperature and pressure, so its length doesn't change. And that was called 1 meter. Wow. Right? And then you could say, okay, this portion, 100th of that is a centimeter. 1,000 of those are a kilometer. Right? So you have to compare it to something. I think now the definition is in terms of speed of light. What we know, how much it goes in 1 second. And then with relation to that, we can figure out what a certain length is. Right? So if I want to say this position, I need a reference. Right? Otherwise, this point could be anywhere on this line if I have no reference. So I have to have a reference, which usually I call the origin. Right? Now I can say, okay, where is this? If I call this as 0, and it's to the right of it, I call it positive. On the left, I call it negative. And then this distance is its position, x. When its position changes, that is the displacement. Right? If it goes from here to here, then that is the displacement. Since it's staying on a straight line, then it cannot like go off in any other direction. Displacement and the distance are the same, except displacement could be positive or negative. If it went left, then the displacement would be negative. Average velocity is displacement divided by time taken for that displacement. There is also the concept of instantaneous velocity. So this may be written as delta x over delta t. And if the velocity is constant, then these things become the same. If it's constant, that means every moment it is the same velocity, right? Then these will be the same things. But if velocity is not constant, then the instantaneous velocity can be changing at every moment. It's the limit of the average velocity at that point if the interval goes to 0. Yeah. Instantaneous velocity. And if it can change, then it will be a function of time, right? Then velocity can change with time. Average acceleration is the average rate of change of velocity. So delta V over delta T. Now, these are the magnitudes, but since this will come positive or negative, that this is a vector. Each of these displacement is a vector, velocity is a vector, and acceleration is a vector. But since we're working only in one dimension, all you will get is a plus or minus there. And instantaneous acceleration is v over dt. If we're talking about constant acceleration, then this will be constant in that case. If there is constant velocity, then acceleration is 0. There is a set of equations that come out if we want to study constant acceleration in one dimension. That also covers zero acceleration if you're moving in uniform motion. Why is this very useful? Because it applies to the case of gravity, right? You drop an object and it is in free fall, then the acceleration due to gravity is referred to as g. It's a vector pointing downwards, which is 9.8 meters per second square. Right, the units you can begin to see here. Delta x is meters, delta t is seconds. And if you're talking about accelerations, delta v is change in velocity, so still this meters per second. So this is meters per second squared. So x is your position. So let's say your position is x0 when time was 0. Time 0 means that's when we start measuring the elapsed time. And at later time, position is x. So x is a function of time. And at time 0, it is at x sub 0. Right? So if you want to find velocity, v, or v sub x. Sub x is useful if you start studying in 2 dimensions. Right? So this is that is dx over dt, right? V dt equals dx, right? And if you go from time 0 to t, so at 0 it is x sub 0, and later it is at some position x, which we can say x final, let's say, at 0 and final. And here, time 0 to t, time is going 0 to some time t, right? Remember what is this? If it is a velocity time graph, it is the area under the curve, right? And the right hand side is xf minus x0. So the final position is the initial position plus the area under the velocity time graph. That area is this. This area is giving you the displacement, right? Because you were at some initial position, plus the displacement will give you the final position. And we'll come back here to complete this. Let's continue down here. Acceleration is dv over dt. Right? Now we're talking about constant acceleration, means a is constant. In this case, a dt equals dv. And let's say initial velocity was v sub 0, and then the final velocity was v sub f. Time is 0 to t. This is equal to, and a is constant, so what is this equal to? T, right? At minus a0 is at. Vf equals v0 plus at, where time is t is the elapsed time, right? Because we started measuring from 0. So now if we come back here, V at any time, so this is, we said V for F is at final, but at any time V is, this still applies, right? V is V0 plus AT. Vf we said final, but at any moment, that is the final moment. This is x0 plus 0 to t v0, which is constant, initial velocity plus at dt. Velocity at any time is v0 plus at, right? 0 plus half at squared. Final position is initial position plus the distance traveled with the initial velocity and the additional because of the acceleration, because the velocity has been increasing. Sometimes what you will see is they will not talk about t, they'll talk about delta t. And that just means you're not saying I'm starting my time count from 0. You may have be starting your time count from t1 and to t2, right? In that case, it's not 0, it is t1 to t2, and delta t is just t2 minus t1. Right? Similarly, delta x is what we were saying, x final minus x initial. And delta v is v final minus v initial. Right? So if we use that approach, then you can just say, oh, delta v equals vf minus v0 is delta v. And instead of t, I'm writing delta t because the initial time may not be 0. The other one, delta x equals v0 delta t plus half a delta t squared. If you manipulate these two together, we can achieve one other relationship which is also useful, which says the square of the final velocity is equal to the square of the initial velocity plus 2 times a times delta x. If you see delta t is here and here, right? Yeah. If you replace delta t with delta v over a in this equation and simplify, we'll be able to find that. Okay. But you see what's happening here, velocity, acceleration, and time are involved. Here, displacement, velocity, change in time, and acceleration are involved. And in the last one, there is no change in time involved. So these three together give us the equations of motion for constant acceleration in one dimension. Right, so let's look at the graphs as well. Acceleration is dv over dt, so that's the slope, right? And even just looking at this, what's the equation of a straight line? V is the intercept times 0, what's the velocity? V sub 0. So that's the intercept, I can replace that here. What's the slope? Slope is a, and that's our equation for v. And the distance traveled is the area under this curve, right? So if this is the time, the distance traveled is this area, right? It is this rectangle plus the triangle, right? Slope is a. Then what is this? Correct. Right? Which is v0 delta t plus half a, which is the same equation we got earlier, right? So this is from the graph.